Alright nerds, so today we're going to talk about how we produce certain elements, in fact the transuranic elements, and how we make commercially and medically useful radioisotopes. Okay, so what's the point? First we're going to define what a transuranic element is, and then we're going to explain the production of them. Then we're going to explain how we create commercial isotopes, or radioisotopes. Okay, so first we need to say what a transuranic element is. And here are the first three: neptunium, plutonium, and americium. And these are all elements that have more protons than uranium. So they have a greater number of protons than uranium, or a greater atomic number, and Z is greater than 92, so more than 92 protons. What makes them interesting is that they don't exist in nature. They are all artificially produced. And we do this in two ways. We can either do it via neutron bombardment, which is in a nuclear reactor, or a fusion reaction, which is done via either a cyclotron or a particle accelerator. They're the same thing, just different names. So anyway, more on that in a second. So we'll start off with neutron bombardment. Now, again, this happens in nuclear reactors. So basically, we get uranium-238 and we bombard them with neutrons. All right, now, and this gets us up to Z95, so it's just the first three. Now, we're bombarding with neutrons. Now, that's not going to change the protons number, that just changes the atomic mass, so the atomic number shouldn't change, except, first off, not all atoms undergo nuclear fission when we bombard them with neutrons. These are called non-fissible. So fissible ones, F-I-S-S-I-B-L-E, they will go through nuclear decay. They will fall apart. They'll split apart basically once we once we hit them with neutrons. But some don't. And in this case, uranium-238, it is non-fissible. So we can hit it with neutrons. It will absorb them. It will take them in, and they will join it, and then we create new elements. So basically, we place the atoms inside the reactor and then they are bombarded by neutrons. Occasionally, the atom absorbs one, so it hits it and it stays in the middle. Now, this is unstable and it undergoes a beta decay, which C above means C previously. So when it undergoes a beta decay, this means that one of those extra neutrons, because the neutron to proton ratio is too high now, one of those extra neutrons turns into or becomes a proton. So it becomes a proton, which shifts the atomic number up, and it loses an electron. So, as the proton number increases, transuranic elements are created. So uranium-238, as we said, is not fissile. It cannot undergo the nuclear chain reaction. So we place it in the reactor, and the following occurs. So we hit it with a neutron, and then it goes from uranium-238 to uranium-239. This is unstable, and it goes to beta decay, and we now have neptunium, because that neutron's become a proton. So this is where the first transuranic neptunium-239 is produced, and we can also use this to produce plutonium and americium. All right, fusion reaction. So particle accelerators. Basically, to make the larger ones, we have to collide heavy nuclei with high-speed positive nuclei. Now, any nuclei that doesn't have electrons on it is positive, so we use things like helium, carbon, and carbon's heavy, but not as heavy as iron, and we use that as well. So let's have a look. So the positive particles we need to be moving at a super high speed, close to the speed of light, so super high speed, so that they overcome the positive repulsion between the two positive nuclei. So bang, gets in there. So we use particle accelerators to get them going at high speeds. Now, basically, uranium-238 is fused with a carbon particle, or another example we're going to look at, and these are the two that we will talk about in our next lesson. Bismuth-209 is fused with iron-58, and that's super heavy. So let's have a look. So uranium-238 is hit by a carbon atom. This gives us californium and 4 neutrons. Or bismuth-209 is hit with iron. This gives us meitnerium and 1 neutron. Okay, so we get these two large transuranic elements Those neutrons that are present, the neutrons which are ejected, they actually don't interact with other ones because they've got that neutral electric charge. They just shoot on straight past the other isotopes and atoms. They should pass straight through. All right. So the commercial isotopes produced by neutron bombardment. All right. Basically, this is done on a regular basis for both medical and commercial industrial uses. Over here on our right, we have the Australian Nuclear Science and Technology Organisation's nuclear reactor at Lucas Heights. It's for commercial use, so it's actually used to produce radioisotopes. Technetium-99M, and the M is important there, it's produced by neutron bombardment of molybdenum-98, and cobalt-60 is produced by neutron bombardment of the stable cobalt-59. Americium, we use this in smoke alarms. It's also produced there by neutron bombardment of plutonium-241. Now, important to note, this is the only one that can do it in Australia. This is the only nuclear reactor we have. Alright, and that's what it looks like. That's the core, and you can see this is filled up with water down here, and yeah. Alright, so commercial isotopes, particle acceleration. Basically, other isotopes, we produce those using particle accelerators, like the National Medical Cyclotron near RPA in Sydney. Basically, particle accelerators, they spin nuclei, usually small to heavy nuclei, but not super heavy, around, getting faster and faster via magnetic, just adding magnetic pull to it. Eventually, there's collided with heavy nuclei. Okay, and this gives us neutron-deficient radioisotopes. So a linear accelerator sends them in a straight line, cyclotrons send them in a spiral, and the radioisotopes they produce include iodine-131, used for, you pump it into the thyroid and it glows if it's not being processed. Carbon-11, nitrogen-13, oxygen-15, which are all used in PET scans, and those are the ones. Now, the most common ones we're going to deal with, obviously, are the neutron bombardment, but you need to have a grasp on both, and we'll talk about more in our activities to come. All right, top work.